Okay, good afternoon. Right, so today, first we want to continue with modular arithmetic. So then we want to finish the modular arithmetic part, but not the modular algebra part. So algebra part we can do it another day, but we want to finish the modular arithmetic and then do some past paper questions. Okay, if we have time. Okay, right. So modular arithmetic I'm doing very slowly because this is not something you have learned. Actually, this is the only topic other than bit of sequence and series. The only topic that you have not done in your O level. Usually, you get about 2 to 3 questions from modular arithmetic. Right, so maximum 4 questions. Okay, so usually just 2 or 3 questions. Okay. So therefore, if you find modular arithmetic very difficult, still you don't have to worry. As long as you are very good at the other topics, still you can pass it. But if you are going for uh, something like hundreds out of hundreds, so yes, try this also. Now remember, for math subject, you don't get ABC. They just say whether you pass or fail. So just because you are just getting that pass or fail, don't think that you can take it relax. You can take it easy because a lot of students fail maths. Okay, lot of students. Okay, so I don't say that for programming, information system, computer system, but I'm a very realistic person. Right, a lot of students fail maths, not because they are bad at modular arithmetic, but because they don't do even the other topics. Right, so they don't do the questions on other topics as well properly. Okay. Right. So that is why we are doing parallelly the other past paper questions while doing modular arithmetic. Okay. Right. So we discussed the first part of the modular arithmetic basically. So what is modular arithmetic? We discuss it is part of abstract algebra, like the set, ring theory, field theory, and so on. The modular theory is one of those theories. So in your syllabus, we have only module theory. Uh, so then we discuss what is modular arithmetic is. It's basically clock arithmetic. Or when we measure angles, we use the modular arithmetic. So that is why after 360, it's again 370 is again 10, right? 380 is again 20. So in clock also after 12, actually 12 must be theoretically 0. Then you get again 1, right? 1, 2, 3, 4, again 12 or 0, again 1, 2, 3, and so on. So we look at the divisibility. What is mean by A is congruent to B mod n? We say that A is congruent to B mod n if A minus B is divisible by n. Okay, as simple as that. If A minus B is divisible by n, we say that A is congruent to B. For a given number, there can be infinite number of congruent values. Okay, infinite number of congruent values. And also you can get negative congruent values as well. But remember, congruent values are, or modular arithmetic is related to whole numbers. So we don't talk about modular arithmetic for 10.3, minus 1.5, and so on. It's only for whole numbers, so integers. Okay. Right. So we look at the basics of what is modular arithmetic is. Okay. Of course, if it is a positive number, it's very easy. You just say divide 12 by 2, say divide 12 by 5 and see whether remainder is 2. Divide 7 by 5 and see whether remainder is 2. But for negative numbers, it doesn't work. Okay. So remember, for any number, you get a module. Of course, for any number, there can be infinite number of congruent values, but always there's a congruent value between 0 and, if mod p, 0 and p minus 1. Right? So there's always that kind of a congruent value as well. But other than that, there can be any other infinite number of congruent values, both positive and negative. Right? For example, 4 is congruent to minus 8. By minus 8 minus 4, it is divisible by 6 because minus 12 is divisible by 6. Yes, so therefore minus 8 is divisible congruent to 4. But minus 8 is not congruent to 5 because minus 8 minus 5 is not divisible by 6. Right? Minus 13 is not divisible by 6. So therefore minus 8 is congruent to 4, but minus 8 is not congruent to 5. Okay. So then we moved on to modular arithmetic. Okay. So one way of looking at modular arithmetic or the modular numbers is referring to the number line. But remember, modular numbers are not symmetric like this. Right? It can be symmetric for some modes, but not for all. Not for all. Right? For example, here you can see that this is mod 4. Say minus 3 is congruent to 1, but plus 3 is congruent to 3. Right? Because it's 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, and so on. Okay. So therefore, don't think that if the congruent of if say 5 is congruent to 1, it doesn't mean that minus 5 is congruent to 1. You can see minus 5 is congruent to 3. Right. So you have to be very careful about that, because a lot of students think that, of course, if 5 is congruent to 2, then minus 5 is congruent to. No, that is not always the case. It can happen for only for some modes. Right? For positive integers, finding mod is very easy. You just divide and find the remainder. But for negative numbers, it doesn't work. It doesn't work. So then what you have to do is take your number and see which multiple of this, when you take multiple of this, and then you have to always add a positive number, and that positive number is the mod value, which is between 0 and, in this case, 0 and 3. So minus 7 into 4 is minus 28. Now to make it minus 25, you have to add plus 3. So therefore we say that minus 25 is congruent to 3 in mod 4. Okay. In mod 4. So that is that approach works for both positive and negative. Okay. And then we look at some properties. Number is always congruent to itself. That is common sense. Then if A is congruent to B and B is congruent to, then B is congruent to A. If 5 is congruent to 3, then 3 is congruent to 5. That is again common sense. Then if A is congruent to B and B is congruent to C, then obviously A is congruent to C. Okay, that is again common sense. So then, of course, modular arithmetic can be done in normal way for add, subtract, and multiplication, but you can't do that the same way for division. Right? So if A mod n plus B mod n can be written as A plus B mod n. Either you can add and take the mod, or you can take the mod and add. Both work. Both are the same values. Okay. So therefore, you can freely add. Right? 3 plus 2 is 5. 5 plus 4 is 9. But of course, if the value is bigger than your mod value, if you want, you can just find the congruent value or the equivalent congruent value, which is between 0 to your mod. Okay. Right. For example, 9 plus 5 is 14. 14 mod 12 is, if you want, you can just write it as 2 mod 12. Okay. But you can just add it. So similarly, you can just subtract. Right. 16 minus 9 is 7, and so on. And again, if you get negative value or whatever, if you want, you can find the congruent value between 0 to your module value. Then multiplication also we can do as normal, right? But if you want, you can take the mod value again, because 24 is congruent to 0. You can say result is 0 mod 12. Okay. So then we look at another few rules. If A is congruent to B mod n, then A plus C is congruent to B plus C, A minus C is congruent to B minus C, and A into C is congruent to B into C in the same mod. But there's nothing called A divided by C is congruent to B divided by C. It happens for very special cases, but not in general. Okay, not in general. Right. So therefore, if 15 is congruent to 3 mod 6, we can say 16 is congruent to 4. Right. 14 is congruent to 2. Right. So we can add, we can subtract, we can multiply. For example, 30 is congruent to 6. Because 15 into 2 is 30, 3 into 2 is 6. So therefore, 30 is congruent to 6, and so on. Okay. So then we discuss another rule, that is, if A is congruent, A1 is congruent to B1, A2 is congruent to B2, then A1 plus A2 is congruent to B1 plus B2, A1 minus A2 is congruent to B1 minus B2, A1 into A2 is congruent to B1 into B2. But there's nothing called A1 divided by A2 is congruent to B1 divided by B2. There's no such rule. And special case of this A1 into A2 is congruent to B1 into B2 is A1 to the power n is congruent to B1 to the power n in mod 10. Okay. For example, if you know that 14 is congruent to 2 in mod 12. I take mod 12 because you are familiar with that. Then I can say 14 to the power 10 or whatever, right? 15 is congruent to 2 to the power 15 mod 12. So that you don't have to worry. If you want, you can just double check. Okay, so let's double check. What is 14 to the power 15? Of course, it will be a huge number. That is the issue. 14 to the power 15. So 14 to the power 15. That is this number. And it's mod 12. Mod 12. And it is 8. So then 2 to the power 15 mod 12 must also be 8. Let's see whether we get 8 again. 2 to the power 15. 2 to the power 15. And it's mod 12. We must get 8. Yes, it is 8. Okay, so those are simple rules. So if A1 is congruent to B1 mod n, then A1 to the power n is congruent to B1 to the power n mod n. Okay, so that is general rule. So we will be using those rules today to do some calculations. Okay, right. So then we did a simple exercise where if you get this kind of big numbers, we can use that property. For example, we can write this as 99999 minus 2 into 99999 minus 5. Okay. Then of course, this is congruent to 1. Then we therefore, sorry, 99999 is congruent to 0. This is also congruent to 0 because those are divisible by 9. So therefore, 0 minus this minus 1. And of course, you have the minus 5. Minus 1 mod 9 into minus 5 mod 9, which is plus 5 mod 9. And the final answer is 5. So if this big number is multiplied and divided by 9, you get 5. So we can use those rules to make it faster if you don't have a calculator. Right. So remember, when it comes to division, there's an issue. You can divide only if that means you can divide by C only if the GCD of your C and N is 1, or in other words, C and N are relatively prime. Okay, C and N are relatively prime. Otherwise, still you can divide by C, but then you have to divide that by the the GCD of that C and N. The mod value also you have to divide by the GCD of C and N. Okay, that is the rule. Okay, so that we discuss. For example, 18 is congruent to 3 mod 5. Okay, so now you have to check whether 18 can be written as something like 6 into 3, and 3 can be written as 1 into 3 mod 5. Now you have to check whether you can divide it both sides by 3. How to check that? You have to check whether the GCD of 3 and 5 is 1, or 3 and 5 are relatively prime. Yes, see, 3 and 5 are relatively prime. So therefore, you can divide both sides by 3 and say 6 is congruent to 1 mod 5. Okay, mod 5. But if these are not relatively prime, still you can divide, but you have to divide it by this D value. Okay. So this is another example we did. 65 is congruent to 5. So 65 I can write it as 13 into 5. 5 I can write at 1 into 5. Now 5 is a common factor. Okay. So let me mark it as multiplication. So therefore, now you have to check whether GCD of 5 and 10 is 1. No, GCD of 5 and 10 is not 1. Of course, GCD of 5 and 10 is 5. So therefore, now you can't just cancel 5 and 5 and say that 13 is congruent to 1 in mod 10. No, that is wrong. But what is the reason? GCD of 5 and 10 is not 1. Or in other words, 5 and 10 are not relatively prime because it is not 1. The common, the only value that divide 5 and 10, 5 and 10 is divided by 5. So therefore, what you have to do is you can say 13 is congruent to 1, but now you have to change the mod. You have to divide the mod by this GCD value. So that is 13 is congruent to 1, but not in mod 10, but in mod 2. You have to divide 10 by the D value. Okay, D value. Simple as that. Okay, simple as that. So just you have to be familiar with that. Right. So then for some of the batches, I have done the Euclidean algorithm, but I think for batch 4 and 5, this is where we stopped. Okay, so therefore I'll go from Euclidean algorithm. Maybe I think one of you guys, one of the batch, I have done the Euclidean algorithm, but anyway, just take this as a small revision then, because we can do Euclidean algorithm very fast, and then we'll discuss how to find the inverse. Okay, as well. So then we'll do some past paper question as well. Right. So Euclidean algorithm for finding GCD. So this is super simple approach, but don't memorize the algorithm. Right. So that is not an easy task. Don't memorize the algorithm. Just remember there's something called Euclidean algorithm. Right. And then you should be able to apply the algorithm and find do the divisions. Okay, do the divisions. Right. Sorry, find the GCD. Okay, find the GCD. Of course, you already know one way of finding GCD. So what is the one way of finding GCD? Find the prime factors of this. Find the prime factors of this. Okay, let's first do it in that approach. What are the prime factors of 39? Because that is the thing that we learn in the very first day in maths. Right, so let's take the easier one first, 15. 15 cannot be written as power of 2. Therefore, I can write it as 3 into 5. Then all are prime numbers. I can stop it. Then I have to take 39. The 2 is not a factor, but 3 is. So therefore, I can write it as 3 into 1, 3. And 3 is a prime number. 13 is a prime number. Okay. So therefore, now I want to find the GCD of 39 and 15, or 15 and 39. So this is GCD. So therefore, you have to take only if they are common and the lower power. So only common value is 3. There's nothing called lower power. Both are having 1. So therefore, GCD of 15 and 39 is 3. Okay. So the biggest number that divides both these numbers are 3, obviously. Okay. So for this kind of questions, of course, this approach works. But now let's use the Euclidean algorithm to find whether we get the same value as 3. But Euclidean algorithm is more useful when these numbers are very large. Okay, so that is why, of course, this approach, our old approach worked for this one. But old approach is not very efficient for very big numbers. Okay, right. So now we found the GCD of 39 and 15 using the normal approach that you have learned in schools as well. Now let's use the Euclidean algorithm. So I told you don't memorize the Euclidean algorithm, just understand how we can use the Euclidean algorithm to find GCD. So this is how you do it. Take the bigger value. So the bigger value is 39. Write it as multiple of 15. So therefore, first step is you write 39 as multiple of 15. Of course, 15 into 2 is 30. Make it little bit smaller than this number. Okay, so therefore 15 into 2 is 30. Then you have to add 9 because we need 39. So then what we do is we take this number, write it as a multiple of this number. So 15 is 9 into 1 plus 6. You have to keep doing this until you get 0 here. Now you take 9 here. You have to write 9 as multiple of 6. Of course, 9 is 6 into 1 plus 3. So then you have to take 6 here, write it as a multiple of this number, which is 3. 3 into 2 is 6. 6 plus 0 is 6. You don't have to add any number 0. So when you get 0, you can stop, right? And this number is your final answer. This number over this number, because this number came here, right? So the previous value or the current value's right value is the GCD. So therefore, GCD is 3. Yes, earlier also we got the GCD as 3. It's super easy, super easy. So that is why I asked you not to memorize this formula or this theorem. rather just understand how to do it. Okay, let's do one more exercise. You will understand it, right? Perfectly, you will understand. No issue. Right. So do this. So I'll do the first step. So you have to continue and find the GCD. Take the bigger value, that is 1030. Write it as 960 into something. Of course, 1. Then how much you want to add? To make it 1030, 40 and another 30. That is 70. Okay, now take 960 here. Write it as a multiple of 70. Now you have to continue. So when you get 0, the above value is the answer. Right, do it. So even grade 5 students should be able to understand this logic. Right, so now you should get the answer. So 960 is 17 to what? 17 to 10 is 700. So that means more than 10. Okay. Maybe 17 into 12, 0, 840. No, right? So we can add another one, maybe 13. So 17 to 13 is 0, 910. So that means 50 remains. So now I have to take the 70 here. I have to write it as a multiple of 50. So 50 into 1 plus 20. Okay. Now I have to take 50 here. 50 is 20 into 2 plus 10. Now I have to take 20. 20 is 10 into 2 plus 0. So now I can stop. And this is the GCD. Previous step value is the GCD. So the GCD must be 10. So yes, GCD is 10. Okay. So that is how you find it. It's super easy, right? Super easy. Right. So let's move on to another question or another approach or another theory now. Now that is how you find the GCD. You take the bigger number, multiplication of smaller number plus something, then take that number, multiplication of this plus something. When you get 0, the previous step you have to find GCD value. Okay. So you can use it for very big numbers because you can quickly calculate it. And it's a very good exercise because you have done programming. Can you write a program, but you have to use the GCD algorithm. Okay, so just do this as exercise, and if you manage to write the program, Java code, just post it to the WhatsApp group so that we can check whether it's working. So just write a Java method program, static method, say GCD. You can just call it. Okay, so I have opened the wrong thing. So just write a program like this, okay? So just after the class, obviously. So the requirement is something like this. So find a method, it return an integer. You can call it GCD or something. You get two integers, int x, int y, and it must return the GCD of x and y. Assume that you are getting positive integers. You must return GCD of x and y. So then check whether by giving these kind of two numbers, you get the correct value. But you have to use Euclidean algorithm. Right? Don't use any other approach. Just use the Euclidean algorithm and calculate it, and you have to return it. Then you can make it even static method so that you can just call it and check in the using your main method. Right. So just do it as exercise. Okay. And you can post the answer to WhatsApp group, or you can better to post the answer to the WhatsApp group. Okay, but others don't look at the answer until you manage to run code it. Okay, you manage to code it. So this is the approach. Don't look at the definition, look at the approach and see whether you can put it into a program. So that is a very good exercise to check whether you have understood programming. Okay, you have understood programming. Right. So now we'll move on to our. So this is the explanation of this algorithm. Right. So basically, what we try to do is say we want to find the 39 GCD of 39 and 15. We want to see whether how many 15s are fit into the 39. So of course, 2 15s are there. Then this is the remainder. Right. This is the remainder. So that is basically 9. Okay. So that is basically 9. Okay. So then we take this 9 into 6, sorry, 9 into 15 side, and we say check whether how many 9s are going to fit into that. So likewise, we keep trying to make it fit into the smaller part, smaller part, smaller part. And finally, we get that GCD value. Try to understand the idea or logic behind this algorithm as well. Okay, but it is not a must. That is just for your information, right? So if you are really curious how this works, basically the idea is you just make it smaller and smaller and see whether which square is going to fit into both these values. Okay. Right. So now we'll move on to our next topic. All these are in your note, UCSC note. Because we know now, just because last year they have not asked any of the question from modular arithmetic, it doesn't mean that this year they don't ask, because 2021 there were two questions, 2020 again there were 2 questions. Okay, so it looks like 2022 no question, but who knows, maybe this time they may ask 4 questions or maybe another 2 questions. Okay. Right. So let's move on to our next subtopic, Firm's little theorem. Right. Firm's little theorem. Firms is a mathematician, so he came up with different theorems. Firm's first theorem, Firm's last theorem, and so on. So this is called Firm's little theorem. Okay. So again, don't worry too much about the definition. Just concentrate on using the theorem in practical situations. Okay. Right. So what the Firm's little theorem says, if P is a prime number, okay, and A is any integer, right? A is any integer, Firm says that A to the power P is A mod P. Okay. A to the power P is, last year there were only 20 questions. Yes. Is it only 20 questions last year? That means they have reduced the number of questions. Okay, let's double check. Last year, yeah, just 20 questions. Yeah, so they had even reduced the number of questions as well last year. Okay. Yeah, but again, I'm checking whether there are any modular arithmetic questions. So far, no. So actually, last year paper looks very simple paper. It looks like very simple paper compared to the, of course, other papers are also not that challenging, but this, I don't see any reason of how can student fail this kind of paper, but don't assume that you will get the similar paper, right? So you might get again questions with lot of sequence and series, and here not much sequence and series questions also. Okay. Yeah, not much sequence and series questions also. It's pretty much a normal paper. Okay. Right. Anyway, it doesn't mean that you will get similar paper, okay? Because these are in your syllabus, these are in your notes. Right. So what the Firm's little theorem says, if P is a prime number, if your mod D is a prime number, right, then A to the power P is congruent to A in that mod P. Okay. A to the power P is congruent to A in mod P, but this work only when your modulo is a prime number. Okay. So it's something like this. We know that, of course, now you can't take 12 because 12 is not a prime number. Okay. So your mod must be a prime number for this to happen. Okay. So let's take an example. Say we want to find 512 mod 3. Right? We want to find 512 mod 3. Now you have to find whether, right? Is it a power of 3? Is it a power of 3? You have to do a bit of guessing. And yes, 512 is 8 to the power 3. Okay. So therefore, what you want to find is 8 to the power 3 mod 3. Okay. And you know that 3 is a prime number. So if 3 is a prime number, we can say that 8 to the power 3 mod 3 is same as 8 mod 3. Right? 8 mod 3. That is what says a to the power p is congruent to a in mod p as long as p is a prime number. Of course, 3 is a prime number. So therefore, 8 to the power 3 is congruent to 8 in mod 3. And 8 to the power 3 is 512. So therefore, now I know that 512 in mod 3 is same as 8 mod 3. And 8 mod 3 is because this is a positive number. When 8 is divided by 3, what is the remainder? That is 2. So therefore, final answer is when 512 is divided by 3, the remainder is 2. So 512 mod 3 is 2. 512 mod 3 is 2. So this is how we use Firm's little theorem. Firm's little theorem. Super easy. Super easy. But this must be a prime number. If it is not a prime number, you can't use Firm's little theorem. Okay. So just try to write it as a power of this, if possible. If it is not possible, of course, you can't do it. You can't do it. You can't do it in this way. Of course, there can be another way. Right. So do this as exercise. Of course, that is super simple exercise. 6 to the power 5 mod 5. And you know that this is prime number. So therefore, when a to the power p is congruent to a in mod p, when p is a prime number. Of course, you can see this is also 5, this is also 5, and 5 is a prime number. So therefore, this is congruent to 6 mod 5. And 6 mod 5 is 1. So therefore, answer is 1 mod 5. Right, answer is 1 mod 5. Right. Okay. So what's the first little theorem say? A to the power p is congruent to a in mod p if p is a prime number. Okay, if p is a prime number. Right. So there's a special case of Firm's little theorem. Right. Special case of Firm's little theorem. That is, remember, a to the power p is congruent to a in mod p if p is a prime number. So the special case is a to the power p minus 1. Earlier, what is the Firm's little theorem says? A to the power p is congruent to a in mod p if p is a prime number. So the special case of the Firm's little theorem says a to the power p minus 1 is congruent to 1 mod p if p is a prime number, and there's another condition, that is a is an integer not divisible by p. Okay, so that means this value a must not be divisible by p. Okay, so that's the second condition. So if both conditions are satisfied, you can say a to the power p minus 1 is congruent to 1 mod p. Okay, so p must be prime, and also a must not be divisible by p. Okay, a is an integer not divisible by p. A must not be divisible by B. Okay. Now we can use that theorem as well. Say we want to find 64 mod 7. How can you find it? Of course, 64 mod 7 can be easily found because 64 divided by 7 is, say, 10 is 70, 9 into 7 is 63. So therefore, this value is, we know that answer is 1. But let's use the firm's little theorem and see whether we can do it like that. Because in the exams, they might give not 64, something like 3,000 something, 5,000 something, or 20,000 something. Right? So remember, 7 is a prime number. So therefore, there's a possibility of applying Firm's little theorem or its special case because 7 is a prime number. So the Firm's little theorem says, the special case say, a to the power p minus 1 is congruent to 1 in mod p if p is a prime number and a is not divisible by p. Okay. A is an integer not divisible by p. Okay. So therefore, what we can do is see whether is this a power of 6 because this is 7. Is this a power of 6? Because this must be p minus 1. Yes, 64 is 2 to the power 6. So therefore, I can write this as 2 to the power 6 mod 7. 2 to the power 6 mod 7. And of course, 2 to the power 6 mod 7 is 1. So it is congruent to 1. Because when this is p minus 1, when this is p minus 1, it is congruent to 1. When this is prime number and a does not divide p. Of course, a does not divide p. So therefore, this answer is what? Answer is 1. So therefore, 64 mod 7 is 1. Right. Try to do this one. The studying can make 6 to the power 4 mod 5. Calculate it. Don't use calculators. So what you must know is a to the power p minus 1 is congruent to a mod p if p is a prime number and a does not divide p. See whether you can write it as, of course, it is already the power of 4, right? Do it. So this must be prime. Already this is prime. And this must be 1 less than this. You can see already that is there. Then where you are. So when this must be a prime number. This power must be 1 less than this. 1 less than electric. So therefore, what is the answer? Answer is 1. Because a to the power p minus 1 is congruent to 1. Special case of Firm's little theorem. So answer is 1. Okay. Answer is 1. This is okay. I will make question question okay, this is 2021 question 25. Example 3 right. So this is okay. Now this kind of a question you can't do if you don't know how to use Firm's little theorem or its special case, because this is a huge number. Either you need a calculator or you must know you must be able to apply the Firm's little theorem. Okay, again check the first condition. This must be prime number. Of course, this is a prime number. So that first condition is satisfied. So the Firm's little theorem special case says a to the power p minus 1 is congruent to 1 in mod p if p is a prime number. Of course, 19 is a prime number, and a does not divide p. Okay. So, but unfortunately, you can see that it is not 18 because p minus 1 means 13 to the power 18. This is not 18, this is 36. This is 36. Okay. So therefore, what we have to do? But that is fine because you can write 36 as 18 into 2. So therefore, I can write this as 13 to the power 18 to the power 2 mod 19. I don't change the value, right? 18 to the power 2 is 36 because when you multiply, you get 36. So now I can write it as, now I know using Firm's little theorem, 13 to the power 18 is 1. 13 to the power 18 is what? Using Firm's little theorem because 19 is prime and this is 18. And of course 13 doesn't divide 19. So therefore this is 1. And its square is 1 square. And 1 square is 1. So therefore answer is what? Again 1. Okay, again 1. So 36 I can write as 18 into 2. So therefore 13 to the power 36 I can write it as 13 to the power 18 into 2. Right? Or I can write it as 13 to the power 18 to the power 2. Okay. And we know that 13 to the power 18 is congruent to 1 mod 19 using the Firm's little theorem special case. So therefore 13 to the power 18 is 1. So therefore 1 squared is again 1. So therefore this is 1. Okay. So therefore final answer is what? 1. මෙතන පාවිච්චි කරපු අනිත් රූල් එක මොකද්ද? මතකද අපි රූල් එකක් කතා කරා මෙන්න මෙතන. මෙන්න මේ රූල් එක. A to the power n is congruent to, sorry. A to the power n is congruent to B to the power n. If A is congruent to A1 is congruent to B1, A1 to the power n is congruent to B1 to the power n. ඔන්න ඔය රූල් එක තමයි පාවිච්චි කරේ. අනිත් රූල් එක. හරි. Okay, so let's do one more question, then we'll do the past paper question. Okay. Try to do this one. Then තනියෙන් කරන්න. 13 to the power 39 mod 19. And good news is 19 is a prime number. I will tell you the good news. That means there's possibility of applying Firm's little theorem. But Firm's little theorem can be applied if we are talking about 13 to the power 18. Then 39 කියන එක 18 වලින් හදා ගන්න පුළුවන් වෙනවා. Right? So remember, Firm's little theorem special case says 13 to the power 18 is congruent to 1 in mod 19. Because this must be, if this is P, this must be P minus 1. So that is what we are going to use. But this is 39. But we can write 39 as 18 into 2, that is 36, okay, plus 3. So therefore, I can write this as 13 to the power 39 is congruent to 13 to the power 18 into 2 plus 3 mod 19. So I don't change. Just I write 39 as 18 into 2 plus 3. So this I can write it as 13 to the power 18 to the power 2 into 13 to the power 3 mod 19. Okay. So that I can write. Remember, when you have multiplication and mod, right? When you have A, B mod then, we rule then that can be write as A mod 10 into B mod 10. Mod අරගෙන වැඩි කරත් එකයි වැඩි කරලා mod ගත්තත් එකයි. ඒක එකතු කිරීමටත් හරි අඩු කිරීමටත් හරි වැඩි කිරීමටත් හරි. So therefore this is a multiplication. So therefore I can write this as මම මේ line මෙහෙට ගේනවා 13 to the power 18 to the power 2 mod 19 into 13 to the power 3 mod 19. And we know that 13 to the power 18 mod 19 is what? Firm's little theorem special case. And it's any power 1 to the any power of 1 is again 1. So therefore this is 1 mod 19 into 13 to the power 3 is not a very big number compared to 13 to the power 39. Right? So that let's calculate. So 13 into 13 is 9,313,9,669. And again, I have to multiply it by 13, because I need 13 to the power 3. 169 into 13 is 9 into 3, the 2, 27, 2, 6 into 3, 18, 20, 2 remains. 3 into 1 is 3, 3 plus 2 is 5. Then this is just 169. 2,197. Mod 19. And we know that 1 mod 19 is 1 into what is 2,197 mod 19. Just divide 2,197 by 19 and calculate the remainder. That is not as big as 13 to the power 39. 2,197 divide by 90. 119, 29, again 19, that is 10, 107. Kiya ked? 5. 9 into 5 is 45. 45. 4 remains. 5 plus 4 is 95. So 7 minus 5 is 2. 10 minus 1 is 12. So අපිට එනවා කීයක් එනවද? 12ක් ඉතුරු වෙනවා. 19 බෙදුවම 12ක් ඉතුරු. So that means 1 into 12. Remember the remainder is 12. So 1 into 12 is 12. So therefore final answer is 12. Right? Final answer is 12. අපි ඉස්සර උත්තරේ හරිද කියලා බලමු. Yes, final answer is 12. මේක වෙනම හෙව්වා. මොකද මේක 19 බෙදලා ඉතුරු ගණන් හොයාගන්න පුළුවන්. දැන් මේ ගණන් දෙන්නේ ඔයාලට බයද කියලා බලන්න. හරි මොකද බය අයව අපිට බෑ ඉංජිනේරින් වලට එකයි යන්න. දැන් බය මිනිස්සෙක් එක්ක ගිහලා අඩු ගානේ අර වික්ටෝරියා වේල උඩ ඊට ගන්න කිව්වත් මිනිහා කලන් දාලා වැටේ. ඉතින් කොහොමද වික්ටෝරියා වේල හදන්නේ? නේද? ගුවන් යානයක් දිහා දැක්කම මිනිහට කලන් තියද? ඉතින් කොහොමද එරොනොටික් ඉංජිනේර කෙනෙක් කරන්නේ? තට්ටු 50ක විතර බිල්ඩිමක් දැක්කම මිනිහට කලන් තියද? එහෙම බෑ ඉතින් නේද? ලොකු ගණන් හදන්නේ ඒකයි. ලොකු ගණන් හදලා බලනවා බය ඇත්තට ඔයාගේ බය නැති කරන එක නෙමෙයි අපි කරන්නේ. බයව හලලා යනවා. නේ. එවරස් නගිනකොට එවරස් නගින්න ඇගේ හත්තිය තියෙන්න ඕනේ. ඒතර ඇගේ හත්තිය නැති අය පල්ලෙන් තියලා නේද? මොකද හරේ තියන් යන්නේ නැහැ. හිතේ හයිය තමයි දැන් බලන්නේ. හිතේ හයිය කොච්චරද කියලා. Right. So that is how you do it. දැන් අර past paper question එක කරන්න පුළුවන්ද බලන්න. දැන් මේක කරන්න බලන්න. So this is 2021 question 25. Again, good news is 17. මේ අහන්නේ divisible by 17න් බෙදුවම කීයක් ඉතුරුනවද කියලා අහන්නේ මොකද්ද? මේ අහලා තියෙන 2 to the power 18 mod 17 කීයද කියලා තමයි වචන වලින් අහලා තියෙන්නේ. The good news is 17 is a prime number. දැන් කරා. දැන් තමයි ඉගෙන ගත්ත දේවල් ටික පාවිච්චි කරන්නේ අපි. චූටි චූටි අය ඉගෙන ගත්තා නේද? අර රූල් එක මේ රූල් එක කියලා. දැන් මේක පාවිච්චි කරලා ගණන් හදන්න. දැන් මේ ගාන හදන්න බැරි වුණා කියලා දුක් වෙන්න එපා. හරි ඔයගොල්ලෝ you are new to the modular arithmetic. So therefore maybe one or two will do it. But others you have to try. It's a struggle. So after sometimes you will feel like okay, I can do this kind of a thing. Initially it's a struggle. Right. So we know that 2 to the power 18. So that is what we want to find. 2 to the power 18 mod 17. What we know is 2 to the power 16 mod 17 is 1. This is congruent to 1. But this is not 16, this is 18. So therefore try to write 18 as a power of 16. Okay. And we know that 18 is 16 into 1 plus 2. ඕක තමයි කරන්න තියෙන්නේ. So this is a technique. Right. ඔය technique එක තමයි දාන්න තියෙන්නේ. සමානලාට මේව එකතු කරන්න දෙන්නේ නැහැ. මේව වැඩි කරාම ගාන හැදෙනවා. සමානලාට එක් තව ගාන එකතු කරන්න වෙනවා. So therefore now I can write this as that is 2 to the power 18 mod 17 as I can write it as 2 to the power 16 into 1 plus 2 mod 17. I don't change the values. අන්නනේ maths කරන කට්ටිය හරි අසාධාරණ වැඩ කරන්නේ අසාධාරණ වැඩ දැක්කොත් එහෙම කෑ ගහලා එනවා මිසක් හරි සාධාරණ වැඩ විතරයි maths වල කරන්නේ. So 16 into 1 is 16, 16 plus 2 is 18. Okay. Or just 2 to the power 16 plus 2. So now I can write this as 2 to the power 16 into, because this into 1 is 1. 2 to the power 2 mod 17. Because indices rules. 2 to the power 16 into 2 to the power 2 is 2 to the power 16 plus 2. 16 plus 2 is 18. Change කරන්න හරි. හොරයක් බොරුවක් පංචාවක් මුකුත් නැහැ. Now this is a multiplication. Multiplication of a mod is same as mod of individuals. මතකනේ? AB mod n is same as A mod n into B mod n. අර අපි දැන් රූල් එකක් කිව්වේ කලින්. එකතු කිරීම අපිට බෙදීම විතරයි ඒක වර්ධින්නේ කියන්නේ. Now therefore I can write it as 2 to the power 16 mod 17 into 2 to the power 2 mod 17. And 2 to the power 16 mod 17 is what? Firm's little theorem special case. When this is P and this is P minus 1, of course 16 is not divisible by 2 and the 17 is a prime number, so therefore this is 1. And 4 mod 17 we know. 4 mod 17 is 4. Right? So therefore final answer is what? This is 1 and 4 mod 17 is 4. Therefore 1 into 4 is 4. Final answer is 4. Final answer is 4. Yeah, 4 mod. So final answer is 4. බලමු answer එක තියෙනවද කියලා උත්තරේ ප්‍රශ්නේ 2021 question 25. 2021 question 25. Answer is B. B is 4. Right? B is 4. So that is 2021 question number 25. Okay. දැන් ඊට වඩා අමාරු question එකක් දෙන්න. දැන් කරන්න ඕන. මේක අපි කොහොමද කරන්නේ දැන්? මේක කරන්න දැන්. දැන් වැඩේ අහුවෙලා නම් ටක් ගාලා කරන්න පුළුවන්. Find 13 to the power 39 mod 19. Good news is 19 is a prime number. Okay, sorry, we did this question, right? Sorry. So let's do the next one. Yeah, we did this, okay? Right, do this one. Okay, this is a slightly different question. Okay, this is slightly different question. So you have to think differently for if you want to do this one. So therefore, anyway, we will do this question also. But I don't think that they will give this kind of a question. But anyway, let's do it. No, this is similar question. Yeah, similar question. So you should be able to do it the same way because 17 is a prime number, right? Yeah. Do this. Yeah, so this is similar question. 100% similar question as previous. And 17 is a prime number, 2 is not divisible, 2 doesn't divide 17. So all the conditions are satisfied. But unfortunately, you no, that's fine, right? 2 to the powers are ගන්න පුළුවන් දෙකේ බල දෙකේ 10 ගියත් 1024යි බය නැතු කරා. ටිකක් ලොකු බලයක් එයි දෙකේ බල හොයන්න අමාරු නෑ. දෙකේ 10 1024යි. Right. So let's write, remember 2 to the power 16 is congruent to 1 in mod 17. That is what we are going to use. Firm's little theorem special case. And 17 is a prime number. 2 doesn't divide 17. Okay. So therefore we can use, now we want to write 50 as something to related to 16. Right. So that means 16 into something plus something. Of course, 50 is 16 into 3, that is 48. Okay, 16 into 3 is 48 plus 2. Okay, so therefore we can write it as 2 to the power 50 mod 17 can be written as 2 to the power 16 to the power 3 plus 2 mod 17. We don't change anything. 16 into 3 is 48. 48 plus 2 is 50. So now I can write it as 2 to the power 16 into 3 into 2 to the power 2 mod 17, because multiplication is addition. And of course, multiplication can be written as a power. 2 to the power 16 to the power 3 into 2 to the power 2 mod 17. And we know that 2 to the power 16 is 1 mod 17 and 1 to the power 3 is 1. So therefore this is 1 into 2 to the power 2 is 4 mod 17. 4 mod 17 is 4. So therefore 1 into 4 is 4. Final answer is 4. Okay. So final answer is 4. So let's use our calculator and double check that. Calculate and double check. So let's take scientific calculator. 2 to the power 50. It's a huge number. Okay, now I want to take the mod 17. And it is 4. Right, it is 4. Because when you do a mod 17, always you must get something between 0 to 16. And it is 4. So you can see that Firm's little theorem can be used for its special case. Especially the special case is very useful to calculate the mod value of very big numbers. So එතකොට කාට හරි යන්න පුළුවන් මොලේ හොද නැද්ද මේ ලොකු number වල mod value හොය හොය ඉන්නේ අපිට වෙන වැඩ නැද්ද කියලා. හරි? Especially when it comes to encryption algorithms, we use this technique to create very strong encryption algorithms or make our algorithms very strong, because others will find it very difficult to guess it. Okay. So in your final year, you have a subject called Information System Security. So there you will learn how some of these encryption and decryption algorithms work, like RSA algorithm. So we use these concepts. Okay, we use these concepts. So basically not we, RSA algorithm and a lot of encryption, decryption algorithms use modular arithmetic. Okay. Right, so I have given you few more exercises. Okay, for few more exercises. Now, definitely this one is more challenging because again but the good news is 11 is a prime number, right? So likewise, you have to do it. Write 532 as 11 into something. Sorry, 10 into something, because when it is 11, what you need is 10. Okay, 10 into something and blah blah blah. Okay, so but still you should be able to do it. Okay, right? So I have given you few exercises, and this is a slightly different example. I don't think that they will give this kind of a question, but who cares, right? There is a possibility, right? But so all these examples 1 to 6 use the same technique. But this one is the example 7, example 8, 9, 10 use slightly different techniques. So therefore, doing example 7, 8, 9, 10 is optional. Okay, so most probably they will not give you that kind of a questions, but anyway, I just added it. Right, so if you are interested, have a look at
Yes.
Right. I think one of you have not mute your microphone. Okay, so let me mute everyone.
Hello.
So make sure that you mute your microphone. Okay, sometimes what happens is without your knowing, your microphone is on. Okay, right. So this is, so therefore example 7 onwards are purely optional examples. If you are really interested, you can have a look at those examples. Otherwise, just concentrate on example 1 to 6. Of course, 1 to 6 are just the same technique, different examples. Okay. But anyway, I'll just explain the example 7 in case you are a little bit curious. So this question is different. Of course, the first thing is 9 is not a prime number. You know that 9 is not a prime number. So therefore, you can't apply the Firm's little theorem or its special case. But still, you can do this kind of a question because we know that you know what is 8 mod 9. Right? So what is 8 mod 9? So you know that 8 is congruent to -1 in mod 9. Of course, 8 mod 9 is 8, but at the same time, 8 is congruent to -1 because 8 minus -1 is 8 plus 1, 9. 9 is divisible by 9. So therefore, now you can write 8 to the power 100 dash because 8 mod 9 is -1 to the power 100. So 100 is an even number. -1 to the power even power is again +1. Odd powers are -1, even powers are +1. So 100 is even number. So therefore, what you get is +1. So therefore, final answer is 8 to the power 100 mod 9 is congruent to 1. කරගත්තේ කොහොමද? අපි 8 කියන එක ලියාගත්තා. අපි මේ එක කියන නම්බරයට හරි කැමති. 1 ඍණ 1 මොකද කොච්චර පවර් ගියත් ප්‍රශ්නයක් නැහැ. අපි දන්නවා එකේ ලක්ෂ ට්‍රිලියනේ පවර් එකත් එකයි. So therefore, though we can't use the Firm's little theorem because 9 is not a prime number, still we manage to solve it using different approach. Of course, if you are familiar, if you have done these kind of questions, that means you have more and more mechanisms to solve a particular question. Okay. So similar approaches we used in question 8, 9, and so on, but I don't think that they will give you any question of type 8, 9, and 10. Okay, 8, 9, and 10 I feel like it is too much for you guys. So therefore, just do up to example 7. Example 7 උත් බලා ගන්න. මොකද එහෙම එකක් දෙන්නත් පුළුවන් නේ. But don't worry about 8, 9. Okay, so those are little bit too advanced. Advanced කියන්නේ පොඩ්ඩක් වැඩියෙන් හිතලා එන හිතනකොට හම් වෙන ටෙක්නික්ස් ටිකක් තියෙනවා. ඒ ටෙක්නික් වලින් ආයි කියලා මම හිතන්නේ නැහැ. මොකද ගිය අවුරුද්දේ modular arithmetic වලින් question එකක්වත් තිබිලත් නැහැනේ. හරි. So therefore I don't want to make you your life too complicated. Okay. So therefore just concentrate till example 7. Of course 1 to 6 are pretty much the same approach. මේ approach එකේ questions තමයි ගොඩක් අර දීලා තියෙන්නේ. හරි. එතකොට 11 තියුණොත් ඔයා බලන්න මේක 10 වැඩි කිරීම කීය එකක් එකතු කරන්න ඕන. හරි. එතකොට මේ චුට්ට විතරකට සුළු කරලා හොයන්න තියෙන. අනිත් එක ඔයාලට Firm's little theorem එක එකයි කියලා. Right. So any questions up to this point? Don't worry about the example 8 and 9. Okay, I might even remove the 8 and 9 from your note because I feel like it is a little bit too much for you. Okay, little bit too much for you. Let me delete those 2 slides because ඔයාලා ඕනට වැඩි කරාමත් පුළුවට අමාරු වැඩි ඉන්නේ. Right, so this one we will keep. I want to just delete this one. Okay. I'll just keep that, but I will hide it. Okay. I will hide it later. Right. So now we move on to our another part that is find in the modular inverse. මේ જાති questions past papers වල තියෙනවා. අපි past paper question එකක් තියෙන එකත් කරමු මේක කළා. And these are super easy. Okay. So finding modular inverse of a number. What is mean by inverse of a number? For example, what is the inverse of 5? Inverse of 5 is 1 over 5 because when you multiply 5 by 1 over 5, you get 1. So therefore, inverse of 5 is 1 over 5. So that is why we use the inverse as something like this. Because anyway, 1 over 5 is 5 to the power minus 1. So in normal arithmetic, inverse of a number n is 1 over n. Because when you multiply n by 1 over n, you get 1. And 1 is called the identity of the multiplication. And 1 n to the power minus 1 is called the multiplicative inverse. So multiplicative inverse of 10 is 1 over 10. Because when you multiply, you get 1. Because multiplicative identity is 1. Multiplicative inverse of minus 10 is minus 5 is 1 over minus 5. Because minus 5 into 1 over minus 5 is 1. Okay. So therefore, multiplicative inverse of n is 1 over n. That is not modular arithmetic, normal arithmetic. Okay. So then you have something called additive inverse. So additive inverse is, for example, additive identity is 0. Multiplicative identity is 1. Additive identity is 0. So therefore, if you have something like plus 5, when you add how much when you add, you get 0 because additive inverse is 0. That value is minus 5. So therefore, additive inverse of 5 is minus 5. Additive inverse of 7 is minus 7 because 7 plus minus 7 is 0 because additive identity is 0. So therefore, in normal arithmetic, we have what is known as additive inverse, multiplicative inverse. Okay. So therefore, now what are the two things you have to remember? So there's something called additive identity, which is 0. There's something called multiplicative identity, which is 1. So then what is additive inverse? Additive inverse of n is minus n because when you add minus n to n, you get additive identity, which is 0. What is the multiplicative identity of n, which is 1 over n, because when you multiply n by 1 over n, you get the multiplicative identity, which is 1. So therefore, minus n is the additive identity of n. 1 over n is the multiplicative identity of n. So this is a concept. It's a definition. Because these are very interesting features that we can use in some other concepts in maths and science. And of course, this is not rocket science. This is very simple thing. So therefore, what is the multiplicative inverse of 3? 1 over 3. What is the additive inverse of 3? Minus 3. Because plus 3 minus 3 is 0. Because 0 is the additive identity. 3 into 1 over 3 is 1. 1 is the multiplicative identity. So we get the multiplicative identity when you multiply 3 by 1 over 3. So therefore, multiplicative inverse of 3 is 1 over 3. Additive inverse of 3 is minus 3. So therefore, multiplicative inverse of n is 1 over n. Additive inverse of n is minus n. Because this results in 1, this results in 0. Got it? Okay. Right. So now we can extend. So this is additive inverse of n is minus n. Multiplicative inverse of n is 1 over n. Because additive identity is 0, multiplicative identity is 1. Now we can extend this concept of inverse into modular numbers. Modular arithmetic. Okay. So this is let's look at what is the inverse value of a modular number if the mod is 5. This is just the example. We just took 5 as example. You can extend this idea of mod 6, mod 3, mod 8, mod 10, mod 12 or whatever. Now first let's look at the additive identity. Additive. And later we'll look at the multiplicative identity. සාමාන්‍ය exam එකට ඕන වෙනවාට multiplicative identity. In mod 5, the possible values are the small values are 0 to 4. So we just write those 4 values here and we write the same set of values in the other row level as well. Now, what happens when you add 0 and 0? That is 0. 0 and 1, 1. 0 and 2, 2. 0 and 3, 3. 0 plus 4, 4. 1 plus 0, 1. 1 plus 1, 2. 1 plus 2, 3. 1 plus 3, 4. 1 plus 4, 5. But 5 is congruent to 0 in mod 5 because we are doing mod 5 arithmetic. 2 plus 0, 2. 2 plus 1, 3. 2 plus 3, sorry, 2 plus 2, 4. 2 plus 3 is 5. 5 means 0. In mod 5, 5 is 0. And 2 plus 4 is 6. 6 mod 5 is 1. So rather than 6, we can write it as 1. So similarly, 3 plus 0 is 3. 3 plus 2 is 5. 5 is 0. 3 plus 3 is 6. 6 is congruent to 1. And so on. So this is 4 plus 0 is 4. 4 plus 1 is 5 is congruent to 0. 4 plus 2 is 6. 6 is congruent to 1. 4 plus 3 is 7. 7 is congruent to 2 and so on. Now you can find what are the additive inverse when it comes to mod 5. So for 0, when you add another 0, you get 0. So therefore additive inverse of 0 in mod 5 is 0. Additive inverse of 1 is 4 because 4 plus 1 is the 0. Mummy බලන්නේ 0 authentic. Additive inverse of 2 in mod 5 is 3 because 2 plus 3 is 5, 5 is 0. Additive inverse of 3 is 2 because 3 plus 2 is 5, 5 is congruent to 0. Additive inverse of 4 in mod 5 is 1 because 4 plus 1 is 5, 5 is congruent to 0. Now you know that additive inverse of 0 in mod 5 is 0, additive inverse of 1 is 4, additive inverse of 2 is 3, additive inverse of 3 is 2, and additive inverse of 4 is 1. That would additive inverse is symmetric. In normal numbers, additive inverse of 5 is minus 5, additive inverse of 2 is minus 2, additive inverse of 10 is minus 10. But in modular arithmetic, additive inverse is not necessarily the same number. For example, additive inverse of 2 in mod 5 is 3 because when you add 3 to 2, you get 0 because additive identity is 0. And you can see that this additive identity, additive inverse of a mod number is not as straightforward as normal additive inverse. So we can extend the same concept of multiplicative inverse. Multiplicative inverse. So 0 into 0 is 0. Of course, 0 into any number is 0. So therefore, all these are 0. Remember, in multiplication, we are not interested in 0. Rather, we are interested in 1 because multiplicative identity is 1. Of course, this column is also 0 because all are 0. So then what about 1 into 1? That is 1. So that is something I'm interested in because multiplicative identity is 1 in any mod. 1 into 2 is 2. 1 into 3 is 3. 1 into 4 is 4. Next row. 2 into 1 is 2. 2 into 2 is 4. 2 into 3 is 6. But 6 is congruent to 1 in mod 5. So therefore, 6 into 2 is congruent to 1. So therefore, I am interested in that one. Right? So then 3 into 3 is 9. 9 is congruent to 4. Remember, 9 mod 5 is 4. 3 into 4 is 12. 12 is congruent to 2 in mod 5. Last one, of course, this is 0. 4 into 1 is 4. 4 into 2 is 8. 8 is congruent to 3. 4 into 3 is 12. 12 is congruent to 2 because 12 mod 5 is 2. 4 into 4 is 16. 16 is congruent to 1. Yes. So now you can see that multiplicative inverse of 1 in mod 5 is 1 because 1 into 1 is 1. And multiplicative inverse of 2 in mod 5 is 3 because 2 into 3 is 6. 6 is 1. Multiplicative inverse of 3 in mod 5 is 2 because 3 into 2 is 6, which is congruent to 1. Multiplicative inverse of 4 is 4 because 4 into 4 is 16, which is congruent to 1. So you can see it's not very straightforward, right? For example, in mod 5, multiplicative inverse of 1 is 1. Multiplicative inverse of 4 is 4. But multiplicative inverse of 2 is 3. Multiplicative inverse of 3 is 2, and so on. Okay. So how can you find it without just multiply and see? Do we have straightforward way to find the multiplicative inverse of a number in modular arithmetic? Especially we are interested in multiplicative inverse, not the additive inverse, but just I explain the additive inverse because it's related concept. Okay. And the other thing is if you take something like mod 6 and do that calculation, right? 1 into 1 is 1, 1 into 2 is 2, and so on, right? 3 into 1 is 3, 3 into 2 is 6, 6 is congruent to 0. I'm talking about the mod 6. And you will find that for some numbers, there's a multiplicative inverse. For example, 1's multiplicative inverse is 1. But for 2, there's no multiplicative inverse because none of the values give you 1. For 3, there is no multiplicative inverse because 3 into 1 is 3, 3 into 2 is 6, 6 is 0, 3 into 3 is 9, 9 is 3, 3 into 4 is 12, 12 is again 0 because 12 is divisible by 6, 3 into 5 is 15, 15 is congruent to 3. So therefore, there is no multiplicative inverse for 3 in mod 6. And again, there's no multiplicative inverse for 4 in mod 6 because none of these values gives you 1. Right? None of these values gives you 1. So therefore, in some mods, for some values you have inverse, multiplicative inverse. For some other values, you don't have multiplicative inverse. But for some other mods, for example, mod 5, for each and every number, there's a multiplicative inverse. Of course, not for 0, but 1 has a multiplicative inverse, which is 1, 2 has a multiplicative inverse, which is 3, 3 has a multiplicative inverse, which is 2, and 4 has a multiplicative inverse, again 4. For some mods, each number has a multiplicative inverse other than 0. But for some other mods, some numbers has multiplicative inverse and some other numbers, they don't have multiplicative inverse. So that is the first thing you have to understand. In modular arithmetic, for some modulos, each number has a multiplicative inverse. But for some other modulos, only some numbers has a multiplicative inverse and some other numbers, they don't have multiplicative inverse. That is the first thing you have to understand. Okay. So then someone will ask, for which modulos we always have multiplicative inverse? And for which other modulos we have only sometimes we have multiplicative inverse? Okay, so those who have read the note, can someone tell me? For which modulos we always have multiplicative inverse? Bara note take yopa, tanin terukan try karpa. For which modulos, for which module values, always there is a multiplicative inverse for any number. What kind of modulos have always a multiplicative inverse? Anyone? For example, 5 is such a number, such a modulo, because each and every number has a multiplicative inverse. Of course, 0 doesn't have multiplicative inverse in normal numbers also. 1 has, 2 has, 3 has, 4 has. But if you take 6, 1 has, but 2, 3, 4 doesn't have. They don't have a multiplicative inverse. But again, 5 has multiplicative inverse. Okay. Right. So how do you check whether a particular number has a multiplicative inverse? If so, how to find that value? Right. So this is another interesting problem in mathematics, modular arithmetic. Finding the inverse of a number for a particular module, for particular module mod value. Okay. Right. So we will look at three different approaches to find this. Of course, it's good to have three approaches rather than one. Okay. So then once you do this, your module arithmetic part is over. Then you have the module algebra part, which is a very small topic. Okay. Right. So we can use three approaches to find the multiplicative inverse of a number. If it exists, of course. If it doesn't exist, of course, we can't find. Not every number has a multiplicative inverse. Only some numbers have multiplicative inverse. Okay. Right. So the first approach is the easiest approach, where we use the Firm's little theorem or its bit of variation to find the multiplicative inverse. But Firm's little theorem can be applied only when your module value is a prime number. Right? If your module value is a prime number, say P, say we have a number called A, its inverse is equal to A to the power P minus 2 mod P. So that is how you find the inverse of a number using Firm's little theorem. මේ වෙන කතාවක්. මේ ඇවිල්ලා කියන්නේ congruent කියලා නෙමෙයි. මෙයාගේ inverse එක මේ number එකට සමානයි කියලා. But remember, we can apply the Firm's little theorem to find the multiplicative inverse only when the module is prime. Okay. And also when the module is prime, for any number, there is an inverse number. All number එකට inverse number එකක් තියෙනවා. prime නැති වුණාම තමයි සමහර numbers වලට තියෙනවා, සමහර numbers වලට නැති වෙන්නේ. දැන් මතක 5 කියන එකට හැම එකටම inverse එකක් තියෙනවා. Because 5 is a prime number. But 6 is not a prime number. So in that case, some numbers have the module inverse, some other digits they don't have an inverse. ඒකත් මතක තියාගන්න. If the modulo is prime number, each number has an inverse, multiplicative inverse. But if the modulo is not a prime number, some numbers have the inverse, some other numbers in that module, they don't have inverse. Okay. But Firm's little theorem can be applied only for the prime modules. Right. So let's say we want to find inverse of 3 in mod 5. Of course, 5 is a prime number, so therefore we can use the Firm's little theorem, its variation, to find the inverse value. So the Firm's little theorem says A inverse is equal to A to the power P minus 2 mod P. Right? A inverse is equal to A to the power P minus 2 mod P as long as P is a prime number. In our case, P is 5. So 5 is a prime number. So therefore, what is the inverse of 3? So 3 inverse is 3 to the power P is 5. 5 minus 2 mod 5. Okay, so 3 inverse is 3 to the power 5 minus 2 mod 5. 3 to the power 5 minus 2 is 3 to the power 3. 3 to the power 3 is 27 mod 5. And 27 mod 5 is 2. When 27 is divided by 5, remainder is 2. So therefore, 3 inverse in mod 5 is 2. 3 inverse in mod 5 is 2. We do another වගුයාවේ 3 ගේ inverse එක 2 කියලාද කියන mod 5 වලදී? Yes, 3 inverse, sorry, this one, multiplicative inverse. 3 inverse in mod 5 is 2. Penal. 3 inverse එකයි කියයි කියලාද? දෙකයි කියලා. I think 3 inverse. So therefore, let's look at the third approach now. Third approach. මේක තමයි 324 දෙනේ. So third approach is finding modular inverse by Euclidean algorithm. අපි Euclidean algorithm එක කලිනුත් කතා කරා GCD ගන්න. මතකද අර? ඒකම තමයි මෙතන පාවිච්චි කරන්න වෙන විදිහකට. Okay. And so the Euclidean algorithm is a better solution because it works for both prime and non-prime modules. So therefore Euclidean algorithm is much better algorithm or much faster algorithm and also much wider use algorithm because it works for both prime and non-prime. Okay. So therefore let's look at whether we can first let's look at how to use the Euclidean algorithm and then let's see whether we can use that algorithm to calculate that past paper question. Okay, is this a question in the past paper 17 mod 43 දාලා දී paper එකේ 17 mod 23 නේ මේක තියෙන 17 mod 43 හරි එතකොට මේකත් නෙමෙයි question එක මේක හැදුවම අපිට ගොඩක් යාට අර කරගන්න පුළුවන් වේද හරි so this is little bit tricky so this is how you do it say we want to find the inverse of 17 in mod 43 this is an example okay again පාඩ දාන විදිය දැනගන්න හොඳම විදිය තමයි ගානක් හදන එක right so your first step is take the modular value and write it as a multiplication of this value. Take the modular value and write it as a multiplication of this into a number. Then rest of the stuff you have to add. Say 17 into 2 meter 43 වලට අඩු වෙන්න ඕනේ ටිකක්. ඉතුරු ටික එකතු කරන්න ඕනේ. So therefore 43 is 17 into 2 that is 34. So 34 to make it 43 you have to add another 9. Another 9. Okay. Now you take this 17 and write it as a multiplication of 9. So 9 into 1 is 9. You have to add 8. Well, 9 into 2 ගත්තොත් meter ලොකුයි. So that is 8. Now you take 9. 9 you can write it as a multiplication of 8. That is 8 into 1 is 8 and plus 1. Okay. And when you get 1 you can stop. එතනට එකම වලට නවත්තන්න පුළුවන්. එක එන්නේ නැත්නම් යාට ඉන්වර්ස් එකක් නැහැ. හරි එක එන්නේ නැහැ කියන්නේ ඉන්වර්ස් එකක් නැහැ. ඒකට දෙන්න ඉන්වර්ස් එකක් තියෙන නම්බරයක්. So when you get 1 here you can stop. Okay. Right now you can write 1 as 9 minus 8. පේනවනේ? 9 1 is 9 minus 8. ඔන්න උතරින් තමයි පටන් ගන්න ගාන හදන්න. Okay. Right. Now what we do is we know that 1 is 9 minus 8, right? 1 is 9 minus 8. Now you can substitute 8 as, right? 8 as 17 minus 9. 9 minus 8, right? 9 minus 8. 8 is 17 minus 9. Okay. Then we know that 9 is 43 minus 17 into 2. 9 is 43 minus 17 into 2. අපි දැන් එකක් දාන්න. 9 is so therefore you have 2 into 9 is 43 minus 17 into 2 minus 17. So remember I start with 1 equal 9 minus 8. Okay. Then I took 8 as 17 minus 9. Okay, 17 minus 9. So that is 9 minus 17 plus 9. Then I took 9 as 43 minus 17 into 2. Okay. 9 as 43 minus 7 into 2. So therefore, what we get is 9 minus 17. 17 is 43 minus 17 into 2 minus 17. Okay. So then I can simplify all the 17 values because I am interested in 17. But 17 n on. 17 n on. So then I have 17 into 5 into 433 into 2. And I am really interested about 43 into 2 because since I am interested in modulo 43, multiplication of 43 is always 1. sorry, multiplication of 43 will give you 0. 43 වැඩි කළ number ඔක්කොගේ mod value කීයද? බිංදුවයි. So therefore this is 0. So therefore 17 into 5 or minus 5 will be 1. 17 5න් වැඩි කරාම තමයි අපිට 1යි කියලා එන්න ඕන mod 43 වල. So therefore what is the inverse of 17 in mod 43? It will be minus 5. Right? It's a very tricky approach. Right? It's a very tricky approach, but it work. Right? अब तब एक example लेकर past paper question नहीं करूँगा. Okay, so this is little bit bigger number, and this is 3000. We don't care because Euclidean algorithm work for any mod. So how do you start? Write 3000 as 197 into. අපි question එක කරා. අපි කෙලින් past paper question එක කරමු. ඒක answer එක දාලා නැහැ මෙතන. හරි. මට තාම ඒක add කරන්න අමතකුණා. Right. So let's do the past paper question now. මේ විදිහටම කරගෙන යන්න. So remember we start 43 as 17 into something plus blah blah blah. හරි අපි ඒ step එක කරමු. Right. So now we move on to this question. What the firm's little theorem එකෙන් කරන්න බැරි වුණා ඒක. So let's start. 23 is 17 into 1 plus 6. 17 So then we take 17 as 6 into 2. මේකෙන් වැඩි කරන්න ඕන. That is 12. 12 plus 5. Now I have to take 6. May 17 ගත්තේ then 6 ගන්නවා. 6 is how many 5s? 5 into 1 plus 1. ඔන්න 1 නාව නවත්තන්න. 5 into 1 is 5. 5 plus 1 is 6. ඔන්න 1යි කියලා ආවම දැන් නවත්තන්න. දැන් ඊළඟ පොතට යන්න. 1 කියන එක ලියනවා අපි 9 minus 8 කියලා දැන්. මේක නම් ලියන්න කොහොමද? 1 equal 6 minus 5. Okay? 1 equals 6 minus 5. අන්තිමට මේ 17 කියන එක ගන්නයි හදන්නේ ආ. මේ 17 කියන එක ගන්න ඕන ආයි කරකොල දැන්. And 1 equal 6 minus 5 is 17 minus 6 into 2. අන්තය වෙනස් කරන්නේ නැහැ. 5 is what? 17 minus 6 into 2. 6 into 2. Now I know what is 6 is. අන්තිමට ඔය ඔක්කොම ටික 17 ලියන්න. So 1 equal to 6 minus 17 plus 6 into 2. 6 minus 17 plus 6 into 2. That is 1 equal to 3 times 6. 6 2 6 1යිනේ. එතකොට 6 3යි. minus 17. මම 17 තියාගන්නවා. දැන් මම 6 වත් අයින් කරගන්න ඕන. එයාවත් 17 වලින් ලියනවා. ඒක ඇතුළට 23 ආවට කවන්නේ නැහැ. හරි? ඒක ඇතුළට 23 ආවට කවන්නේ. So therefore now I can write it as 3 into 6. 6 is 23 minus 17. Right? 23 minus 17. 6 is 23 minus 17. Minus 17. So that is 1 equal 3 times 23. 3 times 23 minus method 3 times 17 or minus 3 times 17 and minus 17. That is 4 times 17. Right? So we know that 23 into 3 minus 4 into 17 is 1. Remember, we are interested in modulo 23. So therefore, when you multiply 23 by another number, 23 number එකකින් වැඩි කරාම ඔය සංඛ්‍යාව අනිවාර්යෙන් 23ෙන් බෙදෙනවා. So this is 23 into 3. So therefore this number is always divisible by 23. So therefore this is 0. Right? So what we are interested is inverse of 17. And when so this is all mod 23, okay? So therefore when I multiply 17 by minus 4, because this is 0, when I multiply 17 by minus 4, I get 1. So therefore what is the inverse of 17? Minus 4. So therefore I get that because this is anyway 0. When I multiply 17 by minus 4, I get 1. So therefore inverse of 17 in mod 23 equal minus 4. Then minus 4 මෙතන නැහැ. Minus 4 නැහැ. So now I want to find a number which is congruent to minus 4 in mod 23. mod 23 වල minus 4 ට congruent වෙන බිඳුවත් 21 22ත් අතර නම්බරේ දැන් හොයාගන්න. මොකක්ද ඒ නම්බරේ? මොකක්ද ඒ නම්බරේ? What is that number? Yeah, so we can write it as 23 into minus 1, then minus 23, and minus 23 එක minus 4 කරන්න කියා කිව්ද කරන්න ඕනද? 18ක් නේ? නෑ 18ක් නෙමෙයි. minus 23 එක minus 4 කරන්න 19ක්. 19, right? Minus 23 plus 19 is plus minus 4, right? 23 minus 23 into minus 1 is minus 23. Minus 23 to make it minus 4, I have to add plus 19. Because minus 23 plus 19 is minus 4. So therefore, this is congruent to 19 in mod 23. So therefore, final answer is 19. So therefore, what is the inverse of 17 in mod 23? 19. On උත්තරය ආව. ඉතින් හරිද කියලා බලන්න ඉස්සෙල්ලා. 11th question. 11th question E. Yes, 11th question answer is C. ඔන්න ගේ මන් දීලා උත්තරය හොයාගත්ත නැත්නම් හරි. අපි ඒවයි තව question එකක් කරමුද? හරි. අපිට මේක ටක් ගාලා හොයන්න පුළුවන් මේ online tools තියෙනවා හැබැයි. online tool වලින් අපිට හොයලා double check කරගන්න පුළුවන්. 17 mod inverse of 17 in mod 23. Okay, so let's say inverse modulo inverse calculator. අපිට හොයන්න ඕන modulo 23. So modulo 23, we want to find the inverse of the උත්තරේ තියෙනවා කොහොමද ඒක? Inverse of 17. 17 ගේ inverse එකයි හොයන්න ඕන modulo 23 වල. කීය දෙන්නේ? 90. මොකද අපිටත් ආ. අපි දැන් වෙන එකක් calculator එකෙන් හොයලා අපේ විදිහටත් හොයලා බලමු. හරි? අපේ විදිහට හොයලා බලමු. අපි හිතමු අපිට ඕන inverse එක හොයන්න 12 ගේ modulo 23 වල අපි ඉස්සෙල්ලා උත්තරයක් තියනවද කියලා බලමු. උත්තරයක් තියෙනවා 2යි කියලා. දැන් අපි අපේ විදිහට හොයලා බලමු. right? අපිට 2 කියලා එනවද කියලා. So what we need is inverse of 12 in module 23. Okay? Okay, so let's do it. So we want to find inverse of 12 in mod 23. Okay, inverse of 12 in mod 23. So earlier the question was inverse of 17 in mod 23. කලින් කරේ ඒක. හරි. අද දැන් පටන් ගන්න කොහමද? You take 23 and write it as 12 into something. That is 12 into 1 because 12 into 2 is bigger than 23 plus 11. Okay, හොඳට බලන් ඉන්න. 12 into 1 plus 11. 12 plus 11 is 23. Then we take 12 here. 12, I have to write it as a multiplication of 11. 11 into 1 plus 1. Take a lazy una වැඩේ. එකපාරම step එක ආවා. 11 into 1 is 11. 11 plus 1 is 1. When you get 1, we have to stop. Now I can write 1 as 12 minus 11. Right? 1 is 12 minus 11. මොකද එක තියෙන්න ඕන වැඩි කරාම එක හැදෙන්න ඕන. ඒකනේ inverse කියන්නේ. So then I can write 1 equal 12 minus 11 is, right? 11 කියන්නේ මොකද්ද? 23 minus 11 is 23 minus 12. Okay. So therefore this is minus into minus is plus 2 times 12 minus 23. And we know that 23, remember we have to do it in mod 23. So therefore this is 0. 23 mod 23 is 0. Right? 23 mod 23 is 0. Well, then what about this? So therefore this part is 0. So 2 into 12 is 1 in mod 23. So 12 කියන එක දෙකෙන් වැඩි කරාම එක එනවලු mod 23 වල. එහෙනම් ඉතින් 12 ගේ inverse එක මොකද්ද? 2. So therefore 12 inverse in mod 12 is, right? 12 inverse, sorry, in mod 23 is 12 දෙකෙන් වැඩි කරාම නම් එක එන්නේ. එහෙනම් 12 inverse එක 2 වෙන්න ඕන. බලන්න අපිට උත්තරය 2යි කියලා නේද? ඒක ඉක්මනට ආව මොකද මෙතන නගලන්නුනේ නැහැ. උත්තරය 2යි. හරි. අපි වෙන එකක් ගමුද එතකොට? හරි අපි ගමු මෙතනට පොඩි එකක් ටිකක්. say 15 ගේ mod 15 වල අපිට ඕන say 8 module 8 ගේ inverse එක. Let's calculate. It's 8 + 2 ආපුවම අපි වෙන එකක් කරමු. say 10 ගේ module එක 15. Oh, you can see there is no modular multiplicative inverse for this integer. එයාට inverse එකක් නැහැ. හැම එකටම තියෙනවා කියන නීතියක් නැහැ. Because this is not a prime number. If this is a prime number, every number has a modulo. This time I took 15. So 15 for 10, there's no inverse in modulo 15. So therefore, let's make it a prime number. Prime number. Let's take this as 11. And let's take this as 6. Then අනිවාර්යෙන් එන්න එපා. දැන් මේක කළ බලමු. දැන් මේක කළ බලමු. Right. So how do you start? What is my requirement? My requirement is I want to find inverse of 6. Right? Inverse of 6 in mod 11. Inverse of 6 in mod 11. So how do you start? You write 11 equal 6 into 1. Okay. Plus අයව කීයක්ද? ඒකට කීයක් එකතු වෙනවද? 11 හැදෙන්න. 5ක් එකතු කරන්න. Okay. So then we take 6. How many 5s? 5 into 1 plus 1. වැඩේ ඉවරයි. මොකද 1යි කියලා ආවනේ. Okay. So then we write 1 equal, backtrack කරනවා. 6 minus 5. And 1 equal, now I'm interested in 6 because I want to find the inverse of 6. But I want to have only 6 and 11s. Okay. So therefore I want to get rid of 5. 6 minus 5 is 11 minus 6. So therefore 1 equal, minus into minus is plus, that is plus 6. That means 2 times 6 minus 11. So remember we are interested in mod 11. In mod 11 this is 0 because 11 is divisible by 11. So therefore this part is 0. So when you multiply 6 by 2, we get 1. So therefore inverse of 6 in mod 11 must be 2. ඒක තමයි ආවේ. හරි. අර කලින් අපි අර සුදු කරන්න කියලා වරද්ද ගත්තේ. හරි. සුළු කරන්න කියලා වරද්ද ගත්තේ නැත්නම් so that's very easy. දැන් ඔයගොල්ලෝ මේ වගේ ගණන් දෙක තුනක් මේ වගේ මොඩ් එකක් දාලා මේ විදිහට සුළු කරලා බලන්න මේකේ උත්තරේ එනවද කියලා. එතකොට හරි ඔක ඇති දෙයක් නැහැ. So don't think that this question is difficult, right? Only thing is you have to go with the proper approach. අපි තවත් එකක් ඕනනම් කරමු. මේක ප්‍රයිම් වෙන්න ඕනවත් නැහැ. හරි ප්‍රයිම් නැතත් මේක වැඩ කරනවා. අපි ප්‍රයිම් එකක් ගමු. එතකොට අනිවාර්යෙන් උත්තරයක් තියෙනවනේ. say 7. දැන් මේක 15 is not a prime number. මේකට උත්තරයක් නැති වෙන්න පුළුවන්. හරි මේකට උත්තරයක් නැති වෙන්න පුළුවන්. හැබැයි අර උත්තරයක් ආවා. මේක ප්‍රයිම් නොවුනත් මම කිව්වේ ප්‍රයිම් නැති. ඒවට තියෙන්න පුළුවන් නැති වෙන්න පුළුවන්. අපි දැන් මේක කරමු බලන්න. So our requirement is inverse of 7 in mod 15. ඔන්න ඔක දැන් හොයන්න. Inverse of 7 in mod 15. දැන් කොහොමද යන්නේ? So you take 15 as a multiplication of 7. 7 into 1. Sorry, 7 into 2 is 14. මොකද 15 නේ තියෙන්නේ. Plus 1. On the plus 1 now one the value නවත්තන්න පුළුවන් එකපාරට. Because when we get plus 1 we can stop. Okay. Now we have to do the backtracking. 1 equal 15 minus 7 into 2. Right? 15 minus 7 into 2. Remember we are interested in mod 15. In mod 15, 15 is 0 because 15 is a multiplication of 15. So therefore this is 0. So therefore now you can see that I am interested in 7. So 1 is equivalent to 7 into minus 2. Man දැන් මේ minus එක මෙතනට දැම්ම because I am interested in plus 7. So this is 0 in mod 15, but this one minus 7 into 2 is, I just wrote it as 7 into minus 2 because I am interested in 7. So therefore when I multiply 7 by minus 2 in mod 15 I get 1. So therefore what is the inverse of 7 in mod 15? Minus 2. So therefore 7 inverse is minus 2 in mod 15. Have a minus 2 කියලා දැන් උත්තරේ ලියලා හරියන්නේ නැහැ. So we want to find the value between 0 to 14. 0 to 14 number එක ගන්න ඕනේ. ඒක හොයාගන්න කොහමද? ඒක තමයි පළවෙනි දවසේ කරේ. Right? So you write minus 2 is minus 2 into say 15. Sorry. නෑ අපි ගන්න ඕනේ 15 කියලා ගන්න ඕනේ නේද? එහෙමනේ ගත්තේ. මෙයාව ලිව්වා ඔතන අර කලින් එකත් අපිට වරද්ද ගත්තා. minus 25 ඕන නම් අපි ලියනවා minus 25 equal කියලා ලියන්න ඕන. මෙයා හතරෙන් right. So we need minus 2. Minus 2 is 15 into හරි. නැත්නම් කලිනුත් වරද්ද ගත්තා. So minus 2 equal 15 into say මොකද එකතු කරන්න ඕන ධන සංඛ්‍යාව. හරි. එකතු කරන්න ඕන ධන සංඛ්‍යාව. So if I want to make it positive value, to make it minus 2, I want to make it little bit bigger than minus 2 so that I can add it. Okay. So what that is minus 1. Because 15 into minus 1 is minus 15. I want to make this a positive number. So minus 15 plus 13. Remember this is minus 15. Minus 15 plus 13 is minus 2. So therefore now we found the congruent to the minus 2, that is plus 13. So therefore rather than minus 2 I can say plus 13. So that is the answer. හරි. එඩේ අහුණාට පස්සේ හරියා. එච්චර අමාරු නෑ. ඒතර මේ ක්‍රමය හරි ලේසි. So this is මේක හොයාගත්තේ අර පළවෙනි දවසේ ඉගෙන ගත්ත එක. අපි ලියනවා මෙයාව 15 වැඩි කිරීම නම්බරයක්. හැබැයි එකතු කරන්න ඕන තව සංඛ්‍යාවක්. මේක ධන වෙන්න ඕන. මොකද අපිට ඕන 0.14ක් තර නම්බරයක්. ඒ නම්බරේ තමයි මේක -1. එතකොට ඍණ 15යි ඍණ 15ට එකතු කරන්න තියෙනවා තව ධන 14. එතකොට තමයි ඍණ 2 වෙනවා. එහෙනම් මෙයා minus 2 is the answer, but minus 2 is congruent to 13. So therefore the expected answer is 13. Okay. Right. So I hope you got it. ටිකක් හදනකොට අර අපිට දැන් මටත් modular arithmetic ඕගොල්ලොත් එක්ක කරන්නේ අවුරුද්දකට එක සැරේනේ. අනිත් දවස්වල අපි modular arithmetic පාවිච්චි කරන්නේ නැහැ නේ. ඒකයි අර මටත් ටිකක් පැටලෙන්නේ. හැබැයි ටිකක් වෙලා ගියාට පස්සේ බයිසිකලේ පදිනවා වගේ දැන් නම් nothing. දැන් නම් ඕන ගානක් දෙන්න හදලා දෙන්න. හරි? ඕන ගානක් දෙන්න හදලා දෙන්න. මෙතනින් ඕන ගානක් අරගෙන අපි ඕන කැල්කියුලේට් නොකර ඉස්සෙල්ලා කැල්කියුලේට් මේවා කළා මොකද කැල්කියුලේට් කළා බලන්න උත්තරයක් තියෙනවද නැද්ද කියලා. මොකද සමහර ඒවාට උත්තරයක් නැහැ. උත්තරයක් නැහැ කියනකොට මෙතන එක කියලා එන්නේ නැහැ. කොච්චර මේක ලියාගෙන ගියත් එක කියලා එන්නේ නැහැ. So that means so that happens only when your modulo is not a prime number. If it is a prime number, always you get a inverse. If it is not a prime number, sometimes for some numbers you have inverse, for some others you don't have inverse. But this approach, Euclidean approach, always gives you the answer if there is a inverse. If there is inverse. Okay. Right. So now we are done with the modular arithmetic part. So the more challenging, more interesting. Right? So the more challenging, more interesting. පොඩි කන්දක් නගිනවා වගේ නෙමෙයි නේද? ලොකු කන්දක් නැගලා කකුල් අතක ගා ඉන්නකොට නේද? බහින්නත් දැන් කොහොමද කියලා කල්පනා කරගන්න. Right. So that's it about modular arithmetic. So the final topic was finding inverse. Okay, finding inverse. Mathematical thing, yeah. Right. So next time, now we have covered the past papers also. අපි තාම modular අපි එක question එකක් කරේ නෑ. මොකද ඒ question එක තාම කරන්න බෑ අපිට. That is this question. That is a modular algebra question. But modular algebra is easy. Not this one. What question? මේක කරන්නේ දැන් කරා. මේකෙත් තව question එකක්. මෙන්න මේ වගේ question එකක් තාම අපිට කරගන්න බෑ. මේක සමීකරණයක් තියෙන. x කියලා පදයක් තියෙනවානේ. So we'll do how to solve this kind of a question next time. It won't take much time. Maybe 1 hour. So then your math syllabus is over. ඔයා modular arithmetic question එක කරනවා කියන්නේ ඔයා මාර confidence. ඒ කියන්නේ ඔයා යන්නේ චණ්ඩියෙක් වගේ. ඒකට ඔයාට අනිත් අය පේන්නේ නිකන් අර චූටි ගණන් පේන්නේ ත්‍රිකෝණමිතිය ගණන් එහෙම පේන්නේ මොනවද නිකන්. නිකන් වැලි කැට වගේ. එහෙම නැහැ confidence එක build කරන්න ඕගොල්ලන්. හරි. confidence එක build වෙන්න. ඒකට අර modular arithmetic question එකකට ready වෙලා යනවා කියන්නේ ඔයාට මේ question නිකන් අර අපි කියන්නේ නිකන් චූ question. හරි. නිකන් පොඩි උන්ගේ question වගේ පේන්න පටන් ගන්නවා. Right. So we stop at this point. So you have another the batch 4 and batch 5. You have another session at 7 because we have to do a lot of programming topics. Okay. Others you don't have any session today. For others the next session will be Monday 7 to 10. It will be most probably it will be free and open source software. මම batch 1 අයට recordings ටික දෙන්නම්කවත් දෙන්න බැරි වුණා. මම දැන් දෙනවා recordings ටික. අනිවාර්යෙන් ඒ ටික බලාගෙන එන්න Monday එකට එද්දි. මොකද Monday එකදී අපි writer calc කරන්නේ නැහැ. ඔයගොල්ලෝ recording එකක් තමයි දෙන්නේ. හරි? recording එකක් දෙන්නේ. recordings ටික බලාගෙන එන්න. මොකද අපි කෙලින්ම gym කරලා past papers කරනවා. හරි? Right. So we stop at this point.